So today we will we'll start our discussion of a completely new topic. This is the continuation of the previous two lectures when we tried to establish some methods how we can compare two different samples. So I hope you remember that we did this for different purposes. So for example, we want to measure how a given treatment or given experiment influences the outcome of interest. So we did this. For example, if you show two different versions of a web page, which one attracts more customers, something like this. The natural question that arises from that topic is the following. So, okay, we know how to compare two means. What if we want to compare more? What if we want to compare 3, 4, 5, 6 different means? Is there any particular method that is suitable to do so? And the answer is yes. So that's what we are going to do today. So frequently, when you make some experiment, it involves more than two samples. So they may compare several treatments or different levels of a treatment. So for example, when there are some medical experiments, there are usually three groups, not two. One group is the treatment group, one group is the placebo group, and the third group is the control group, which receives no drug, neither placebo nor the tested drug. Well, there are three samples, and we need to compare their population means for each of those samples. In this lecture, I designed something maybe closer to the economy, to the economics. So we will test 4 different technologies of an oil extraction. So suppose that there is an oil company, and this oil company tries to verify which technology is better, is more productive for the oil extraction. And then they take 4 different oil wells, they apply 4 different techniques or technologies on these wells, and they want to compare which oil well extracts more oil. So how can we verify that a particular technology is undoubtedly better than the others? So it's not just due to randomness, right? So we usually must be concerned that the difference arises because of the randomness of this world, and the randomness of our measurements, and the randomness of our sample collection. But we want to be as confident as we want, as we can, that this difference is not because of randomness, but because of a technology used. Like in the previous topic, we want to know that a given treatment makes 2 samples different. Well, we introduced today a statistical method which called analysis of variance. So don't be confused, the name says about variance, but we are gonna compare different population means, not variances. So, but the variance is the key that helps us to do so. And this method is used widely when you want to compare several samples, not 2, but more. And we will use this analysis of variance in econometrics classes as well. So today we will just introduce this method, the logic of this method, so how the calculations are done. And in the next week, we will develop this in more, let's say, sophisticated ways. So I hope you understand the problem. So we want to compare population means for more than 2 populations, 3, 4, 5, and so on. Yes, so this method helps to compare several means of the data coming from different populations, or maybe the same. So that's actually the question. whether the sample comes from the same population or from the different population. So we will start with something which is called a one-way layout or one-way ANOVA. So this is the design of an experiment where independent measurements, which means that we want, as usual, I'm not kind of talking about this all the time, we want to randomly select several observations from different groups. So one group is going to be under one type of treatment, another group is going to be under the other type of treatment, third group from the third type of treatment, and so on. As we told, maybe there are 4 different technologies how we can extract oil, and well, those 4 are different treatments, and we want to take some independent measurements. So, as I said, this technique is a generalization of the techniques for comparing 2 independent samples. And as an example, we will use the following data. This data is not real. This data is simulated, but basically, if you would do this, if you would ever work in some oil company, and if you would like to make something similar, so you will get the real data for the same experiment. So here is the data. Here is the way how we can use the data. For simplicity, I took 10 random observations for each oil well, how much oil was extracted by each oil well at a particular day. So 1, second, the first, the second, the third, and the fourth. As usual, we assume that those observations are independent and they are identically distributed, at least for every particular column, for well 1, well 2, well 3, and well 4. Well, we see that there is some variation in data, so numbers are different, as it normally appears, right? Because, well, when we select some random sample, so this random sample contains different numbers. And what do we want to know? We want to understand whether there is enough evidence in this data to claim that some particular well, for example, well number 3, because you can note that all numbers here are more or less lower than the others, right? So these numbers are like 4 tones and around 4, and this, for example, is less than 4. So is this, for example, is this observation enough to claim that, for example, well number 3 is less productive than the others? That's a question. Well, when we watch, when we look at some numbers, the first problem is that it is kind of difficult to comprehend what's going on there. So we started in econometrics in the exercise session. We started establishing some skills how to visualize data, because when you do some visualization, that's usually better and you can see what's going on there. So how can we visualize this data? Here is some new type of the graph, which is very useful in this case. This graph is called box plot. So let's see what this box plot tells us. So we take those numbers from the previous table, and every kind of box is built for every well. So well 1, well 2, well 3, well 4. What these boxes show us. So let's look at the box number 1, for example, the left one. So these two lines on top and bottom, they show us maximum and minimum values in the data. So let's go here. So what is the minimum? 393, right? So this is the minimum number. What is the maximum? Here, 414. So exactly here, 393, 414. So the line in the middle of the box, this is median. I hope you remember what is median. So median divides all our observations, though this is an empirical median. Empirical median divides all our observations into 50% above, 50% below. So it means that 5 days, this first well produced oil. So the production was larger than this number, something like 400 something, like 03 probably. And half of these days, like 5 other days, the production was lower than this number. So the box itself, this box, and the borders of this box, so the lower and upper border, they identify lower and upper quartiles. So I hope you also remember what are quartiles. Those are 25 and 75% quantiles. So 25% of observations lay below this level, something like 4, and 25% of observations lays above this. So basically, looking at this graph, we can comprehend where is the center of the distribution, of the empirical distribution of this data, right? So the center is here. And we can comprehend what is the dispersion of this data? So how wide all the observations are dispersed around this center. So the dispersion of this well, for example, is much less than the dispersion of this well, of the well number 2. You see that minimum and maximum here are wider. I mean, the range of these numbers is much wider. The median lays below the median from the first well, and the dispersion of 50% of observations is also wider. Well number 4 contains one more interesting thing here, dot, which does not appear in any of these 3. So what this dot shows us? Now the upper line is not a maximum anymore. This is, let's say, normalized value, and the dot is the maximum, which lays far beyond of the what is called interquartile range. So at least at this moment, I am not commenting about the interquartile range. What is this? We will discuss about this a bit later. So basically, this is, let's say, the observation that significantly differs from the other observations. So let's see here. We have 407, 408, 407, 406. So everything is more or less homogeneous, right? So all these numbers are very close to each other. And then we have something very, very far from these numbers, 418. And that's what this box plot shows us, that there is one observation, at least one, because there is one diamond here. One observation which is far from the others. Relatively far. I mean, relatively, because all the other observations are tightly concentrated in very, very narrow interval. So, and when we look at this graph, It gives us some sense. Yes, what?
Why isn't it just included in the upper quantile? I don't get it. It's just 10%.
Well, that's an idea of this box plot. So box plot shows you if the data is homogeneous and if all the observations are, let's say, homogeneous, if they all concentrated around a reasonable interval, then maximum and minimum are showed with these upper and lower borders. So here is the minimum, here is the maximum. But if some observation significantly differs from others, so like it's far from every all the other things, then this observation is identified here with this dot.
Okay, I just
Because
didn't like.
it just shows us a sense. It gives us a sense whether the data is homogeneous or not, or whether we have some how to say, like they're called outliers. We haven't discussed this yet about the descriptive statistics and how to call all the things, but these are the observations that are not, how to say, that are not common in a sense when compared with the whole data.
Okay.
So what we can see from this graph? So first of all, we see that each well, each oil well differs in terms of variability, right? So for example, well number 2 gives us the most variability in terms of the production. So well number 4 is kind of tightly concentrated around center, but there is one outlier, right? So one not standard, non-standard observation. What we also see that variability is visible between these wells, right? So well number 2, well number 1 has a higher median production than, for example, well number 3, and the median production for well number 3 is lower. And here is a question. So does this difference between, for example, well 3 and well 1, does this difference, is this difference attributed to the difference in technology, or this difference is a product of a random sampling? You remember that even if we randomly sample observations, there is a chance to receive a high difference between one and the other sample. So in principle, it's possible in 10 coin tosses to obtain 10 heads. It's possible even though the probability is very low. And that's what we want to test. So this difference between well 3 and well 1, or well 3 and well 4, is this difference is purely random, and taking another sample of observations we will get something close to each other, or this difference is attributed to the different technology used in well 3, well 4, and well 1 and well 2. That's what we want to investigate. So usually we start with this box plot. Why? Because it just gives us an understanding what's going on in the data, instead of kind of peeling at these numbers and probably seeing nothing, because there is a table and it's very difficult to comprehend this table. We look at nicely organized data in this form of a box plot, and we see from this box plot all the necessary characteristics of the data: maximum, minimum, median, first and third quartiles, which is quite enough to understand the data. So now here is our problem. We see that well number 3 is somehow different from others. Well number 4 as well, right? So it is tightly distributed and the median is higher than the others. So to wrap up what we have discussed, given that box plot. So what is the idea of this analysis of variance, or ANOVA? So there are two possible sources of variability in the data. So one source is called variability within oil wells. What is this variability within? This is the variability that we have seen for every oil well, like this dispersion of every box. And variability between oil wells. Variability between is these different levels for each oil well. Like one is higher, another is lower. Well, what we see that box plot shows some variation in the medians among the 4 oil wells, and also some variation in every oil well due to the random sampling, and probably due to just different productivity every day. So that picture suggests, but we are not sure, it just suggests that there may be some systematic differences between the oil wells, and there is less variability in some wells than in others, right? So that's what we have seen. So in this well, variability is higher, and this is lower, and also there is some difference in the levels of production. So one oil well produces more oil than the other in media. So the question is, are these differences in means of the measurements from the various wells significant? Or they are just because of a chance, because of our procedure of random sampling? As usual, as for 2 samples, we ask this question, but now this question considers 4 samples. So, going to some formal definitions. This is a statistical, the formal model of one-way layout, or one-way ANOVA. So suppose we have K populations or treatments. So what is K for our example? How much is K? How many different treatments do we have? 4. Yes. So we have 4 different treatments, 4 different technologies used in oil wells. Well, for every treatment, we have some number of observations, Ni, observations in each. So basically now we have equal number of observations, 10, 10, 10, and 10. But in principle, we can have different number of observations, nothing changes. Well, for every I from 1 to K, so look, with I, we denote the treatment. 1, 2, 3, 4 in our example. And J is the number of observations. So this is the number of row. 1, 2, 3, 4 up to 10 for every oil well. We have the following model. So look, every number that we have there is decomposed in 3 parts. So this is the random variable, xij. This random variable is, so in our case, it denotes the production of oil by the oil well, any oil well. So the subscript ij means that this is the production of oil on ith oil well in jth day. So back to our example. So, and this number is decomposed into 3 parts. So one part is mu, which is overall mean. The other part is alpha I. So this alpha has nothing to do with alpha, which is the size of a size of a rejection region. So this is just another letter. I mean, the same letter, but has another meaning. And look, this is alpha I. So this is alpha that differs only for our populations, for oil wells. And we have also epsilon ij. And this epsilon ij is the part that differs for every observation. For ith well and jth observation in this well. Well, what do we have?
Mu is
mu is constant. It's just a constant.
All wells together, and
yes. So suppose that you are considering all oil wells in the world, and mu is gonna be the mean productivity of oil wells in the world. I mean, for all of them. This is the population mean for like overall population mean.
For all treatments, I mean, yes?
Yes.
And again, sorry, alpha and
epsilon. Alpha is the part that is attributed to the treatment. So I will describe this right now. So I'm gonna describe every part of this formula. So what is xij once again? So this is a jth observation from population or treatment I. So this is just what will we have. This is a random variable that actually when we draw a sample ends up in the form of a number in our table. So xij takes value 392, takes value 369, takes value 404, takes value 407, and so on. So this is a random variable. I have 4 oil wells. I randomly select one well. I randomly select a particular day of production. Go and measure how much tons this well has produced in a given day. So this is xij, just any number from our table. Any number from our table. Now, what is mu? Mu is the overall mean. One constant mean for any number in our table. What is alpha I? Alpha I is the non-random effect of a treatment I. So why do we call this non-random effect? Because we want to verify that increase in productivity is not random, but this increase in productivity appears because of a different technology. Therefore, it must not be random. It must be non-random, right? So that's why we call this non-random effect of a treatment I. And this is attributed only to different treatments. 1, 2, 3, 4. Well, we normalize these effects. Their sum must be equal to 0. This is just mathematical to ascertain that everything is gonna work in a correct way. Well, what is epsilon ij is the random error term, and this must be independent, normally distributed random variable. So this is the crucial point here. As usual, we establish all these methods based on the assumption that the distributions are normal, or we have a considerably large sample that, with the help of central limit theorem, can be justified as normal. So look, this epsilon ij is just a difference from our expectation, and this difference comes because of some other factors. if you remember econometrics, and like our lecture last week, and I hope you remember that we have established something similar. We have established the decomposition of y given x, right? So there was y equals x plus error term. So this error term is something similar. So this epsilon ij is the random error, which appears because of some other conditions. So probably the weather in that day was not good. Probably the people who worked on that oil well were kind of different. So probably, I don't know, something else has changed. So all the other factors that can influence the productivity of this oil well are hidden inside of this error term, random error. Everything except for alpha I. And alpha I is the effect that increases or decreases our productivity because of the different technology used on the oil well. So now, my question to you, if we want to verify that different wells and different technologies are significantly different in terms of their productivity, what do we want to test in this model? Or say it differently, if there is no difference in technologies, what must be special about this model?
There will be no alpha.
Yes, there must not be alpha. So if technologies are not different in terms of their productivity, all alphas must be 0. So two last things, given that these epsilons are normally distributed, expected epsilon is 0 and variance is sigma squared, but this is just a technicality. That's absolutely correct. So why do we create this model? Because if we believe that xij contains these 3 parts, we can formally test whether alpha in the first column is different from alpha in the second column, is different from alpha in the third and in the fourth. So basically, if there is no difference in technology, all alphas must be 0. So that's what we are going to discuss here. Here is a model, and first of all, the expected response to the ith treatment. So what is the expectation of xij? So we will denote this with mu I, mu1, mu2, mu3, mu4, and so on. And this is going to be mu plus alpha I. So we are talking about random variable. The expected value of this random variable is going to be this random variable, which represents the productivity of a particular technology, of a particular oil well. In this case, first, second, third, or fourth. And if alphas are 0, all the alphas are 0. Then mu1 equals mu2 equals mu k. So these expectations will not be different. And I hope you see that now we came to the point where this topic is similar to the previous topic. Because in the previous topic, we wanted to test mu1 equals mu2. Now, with the help of this model, we are testing mu1 equals mu2 equals mu3, mu4, up to mu k. This is the extension of the previous topic, therefore. So, we want to test the null hypothesis that mu1 equals mu2 and so on equals to mu k. So all of them are the same numbers. and they are the same only if alpha i's for all i's are 0. The problem is with the alternative hypothesis, because the alternative hypothesis states that there is at least one pair of mu I and mu I prime, so where I and I prime are different numbers, so 1 and 2, 1 and 3, 1 and 4, 2 and 4, 3 and 4, so on. So some number, some pair of treatments for which these means are not equal. So we see that alternative hypothesis does not specify for which exact pair these means are different. It just says, well, for some pairs, these mean are different. That's all. But at least we can be sure that if we are able to reject the null hypothesis, then there is a difference between some of them, and then we can start looking for this exact pair. So how do we test this hypothesis? So I hope you understand the mechanism. So usually when we have some hypothesis, when we have some population model, in our case the population model is here, what do we want in order to test the hypothesis? We want to find some test statistic, right? So we want to establish some test statistic based on the data. So now the question is, what kind of test statistic we can use here? Because t-statistic definitely is not applicable. Why? Because in t-statistic we used only 2 samples, and it's not possible to extend t-statistic to 3 or 4 or 5 samples. So, and here comes this name, analysis of variance. So we will start with the following thing. So I decided not to go deep into mathematical details, at least some necessary things for you to understand. So the main idea of this ANOVA test is to split the variation in the data into 2 parts. So I started with this idea. So the data varies because of our random sampling process. This is the random error, epsilon. And also the data can differ because of these different treatments. Well, we want to do this. We want to split this variation into the variation caused by the different treatment levels, and we would call this between groups variation, and the variation caused by the randomness of data, and we will call this within groups variation. So how do we do this? So first of all, we will define something which is called sum of squares. We will start with the definition of sum of the total sum of squares. So there are, in different books, there are different notations, so I decided to stick to this, SS total. So the total variation is calculated in the following way. Look, we calculate the overall sample mean, x bar. So for all 40 numbers, if you remember that table, for all 40 numbers, we calculate the sample mean, x bar. Then we calculate the deviation of every number from that table, from this sample mean, and then we square this. So this looks similar to the calculation of a sample variance. If you remember how we calculate the sample variance. The only thing that is not used here is the division by n-1, right? So we don't divide these squared deviations. We don't divide this by n-1. Therefore, this is just a numerator of a sample variance. So this double summation just shows that first of all we do this calculation for every column, and we sum these deviations for every column, And then we have like this for four columns, we have four sums, and then we sum these sums, like this outer summation. So basically, don't panic. This is not difficult. Well, we call this as a tot, a total sum of squares. X bar, as I said, is a sample mean for the whole data. So all our 40 observations in the table, we calculate the sample mean for all of them. And we want to split this expression into two parts. So one part is going to be sum of squares within, and the second part is sum of squares between. So SSW is the sum of squares within groups, SSB is the sum of squares between groups. So look, what it gives us, just try to understand the idea. The idea is very simple. So SS total measures the total variation of our data. So it doesn't matter to which oil well we attribute a particular observation, we just take them like a pooled sample, one sample of 40 observations, and we calculate sample average, and then we calculate these square deviations. So this measures the variation in our sample as a whole. Then, as we said, this variation comes because of two different reasons. One reason is the nature of our random sampling. This is the usual case which we had in all our previous classes. When you see the random sample, and the random sample numbers are different. Why these numbers are different? Well, because we are taking the random sample, and in the random sample the numbers are different. And this part is measured with the help of this first term, SSW. But also, we assume that different technologies lead to the variation in the productivity. And these different technologies can also affect the variability in our data. That's what we have seen in our box plot in these different levels of the boxes. One box is above and the one box is below. And the second source of variability is captured with the help of this second term, sum of squares between groups. Next, if we are able to decompose this SS tot into two parts, how can we test the previous hypothesis? If SSB is significantly large, then different treatments influence the variability in the data, which means that different treatments, different technologies of oil extraction lead to different productivity. If SSB is small, then we don't have enough evidence to claim that different technologies lead to difference in the sample. So the whole difference in the sample is due to just randomness and random nature of data. So that's an idea, and you will see how we will implement this idea. So first of all, how should we decompose this, and how, using data, we should calculate these two parts? What is SSW, what is SSB? So let's do some mathematics. It's gonna be simple, very simple. So as a first step with this sum of squares total, we do the following thing. We add and subtract inside these brackets, we add and subtract the sample average for every treatment group here. Look, I add x bar I and subtract x bar I. What is x bar I? This is the sample average for one particular column. Not for the whole data, but only for one column. So this is x1, x2, x3, and x4 bars. Only 4 numbers we have because 4 columns in our data we have. That's the first step. The second step, what do we have? Let's continue once again. So here we add and subtract the sample average for every particular treatment group, for every particular column, for column 1, column 2, column 3, column 4. Here in the square brackets, we have the sum of 2 terms. This is one term, this is the other term, and we have the square of the sum. I hope you remember from your school how you can factor out the square of a sum. So we are doing this. So we take the square of the first term, the square of the second term, and 2 products of these 2 terms. That's gonna be the next part. Look, what do we have? We have this double summation of a square of a first term. We have this double summation of a square of the second term. And inside we have 2 double summations of the first term times the second term. This is a simple thing that you remember, all of you must remember from your school. A plus b squared equals a squared plus 2ab plus b squared. That's simple. What is next? Let's look at this middle part. What do we have here? Xij are different numbers. So those 40 numbers in our table. Xi bar are 4 numbers, means for every column. Xi bar here are just 4 numbers, and X bar is 1 number. It's a constant. So basically, X bar I does not differ for different j's. This thing is gonna be the same for every j, because j is the row, right? So j is first, second, third, fourth, fifth row, and so on. And for the first, second, third, fourth, fifth row of the first column, we will always have the same number here, xi bar minus x bar. So this is going to be constant. Therefore, we can factor this out of the summation sign. That's the next step here. So first we rearrange, we take this double summation to the left, and here I take this out of the first summation sign. It is not different, it does not differ for j's. It differs only for i's. And now we have an interesting thing. Here, this thing is 0. Because the sum of deviations from a mean is 0. Therefore, the whole term becomes 0 as well. The whole third term is 0. And we are left with only these 2 terms.
Sorry, but why? How the mean of treatment can be not different from the mean of population?
No, they are different, but there are some is, wait, sorry, let me see. Oh my god, these parts are 0. Sorry, not this part, not this. These parts and their sum are 0. Why? Because look, what is here? We are taking 10 numbers. We are taking their average, and then we calculate their deviations from the average and sum over them. So I can demonstrate it if you do.
Okay, this is yes, okay. I think I got it. This part is equals 0.
Look, yes. This is typo, not this part, but this part. Yes, that's true. So look, let me show you. Here is the data from that slide. Here is the data that I have shown you. So what is xi bar here? This is the average for every column. So for example, if I calculate this average, bam, and then we have these 4 averages. And now here, for every I, for example, for I equals 1, I want to calculate the sum of these deviations, x1j from x bar 1. So this is going to be here. For example, I calculate this 413 minus 4045. These are, so these 10 numbers are the numbers that I need to sum here under this summation sign for I equals 1. So what is going to be their sum? 0. Right, so if I change the format. If I do this for every other column, just need to change this thing. Like this and this. You see that all these sums are also going to be 0. So this sum for every I is 0. Therefore, the whole sum is 0. Yes, this is my typo, my bad. This is not the correct thing. So let me change this right. Disappears, and we are left only with these 2 terms, first and second. And if we denote the first term to be the sum of squared within, and the second term the sum of squared between, well, we have what we actually wanted. We decomposed this total sum of squares into 2 parts. So one part, this part, is deviations of in every column from the column mean, from the column sample average. That's what I calculated here in this table. So these are the square deviations from every respective column mean. And the second part, look, these are deviations of these treatment means or group means from the overall average. It must not be I. Again, my mistake. Sample average. Yes. So, so finally we have this sum. We have this decomposition. And the idea of our test that we are going to apply is the following. If this part of the total sum of squares, if this part is large enough, then the evidence that indicates a difference between these mu's is going to be also heavier. That's an idea. So we want to know that SSB is significant part of this SS total. Well, let's first of all see how we calculate all these things. SSW, SSB, and if we have a data, so how to deal with this data, because as usual, I would like you to calculate everything step by step. So of course you can use some software for the calculation, not necessary to calculate everything with hand, but you need to be able to construct every part separately. So I made this table slightly shorter just to fill everything on the screen, but I guess you'll understand the idea. So first of all, we calculate these xi bars. So those are the means for every column. So the average of this column, average of this column, average of this column, average of this column. The overall average, x bar, is calculated as usual. We take all 40 numbers, the whole table, sum over them, 413, 402, blah, 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 up to this last number, 414. We sum over them, divide by 40 by the number of observations, and we have this overall sample mean, 3978. Well, as I said, every particular group sample mean we calculate with the help of the respective columns. And of course, we divide by the number of observations in this column, for example, by 10 or by something else. And the same for every other thing. So I hope that this is clear what is going on here. So the next step, how do we calculate this SS total? Well, we take every number, we take the whole table, all 40 observations, and we subtract from every number the overall sample average, this 3978. From all 40 numbers, square these differences and sum over them. And we have this 09766. So probably you will comprehend this better if I will show you this with the help of Excel, because, well, in Python everything is going to be hidden, all these calculations, so therefore in Excel you see kind of manually what's going on. So let me take this data once again. So I demonstrated you how these differences disappear. So if I calculate sum of squares total, so what should I do? First of all, I want to calculate, make it better, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also we want to make this, well, 1, 4, 2, 3, and 4. Okay. So this is group average, right? And the total average is going to be calculated simply as the average of these all 40 numbers. That's it, 3978. So now, if I want to calculate the sum of squares total, what should I do? I need to calculate the deviation from every number in my data, of every number from my data, from the total average, and I want to square this. So here we are. Here, and 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10, like this. So these are the numbers that I need to calculate here. Then I need to sum over them. And their sum is going to be equal exactly what we have here. That's the total sum of squares. Now, the next step. Let's go here. I want to calculate sum of squares within and sum of squares between. What's going on here? So let's look at the formula. I need to take every number for every particular I and subtract the group average, which means that now I'm doing this for every column separately, and then I sum the results. So what would be here? SSW, sum of squares within. I do this. I take the first column, I take the number 413 minus the group average squared, copy this for only the first column. One, two, so here. Right, yes. So this is only for the first column. I calculate the deviations of this column numbers from the group average. Now I do this for every column. And then I sum the results, all these results. And that's gonna be sum of squared within here. So I showed you here with the numbers. So 413 minus the group average 402 minus group average. Then we go to the, and we do this for all the numbers. Then we go to the second column, 429 minus group average plus 359 minus group average. And then we do this up to the last column. So for example, 414 minus 4092 squared. And then we sum all these 40. There are also 40 elements, but those elements are different. So we calculate how much every observation column deviates from the treatment average or from the group average, which shows us this variability due to the randomness of our sampling, not due to different levels of treatment.
Can I ask in advance if you will upload the Excel table?
I can, yes. No problem with this.
Great. Thank you.
And the last element. So basically the last element we can calculate from this identity, right? So if you want, if you know SS total and if you know SSW, we can simply calculate SSB as a difference. But let's also consider how to calculate this with the help of the formula. So we also want to have here 40 numbers. Why 40? Because for every column, 1, 2, 3, 4, and for every line from 1 to ni, so from 1 to 10, we want to calculate these differences. But look, these differences are the same for every column. For the first column and every line, I will have 10 similar numbers. xi bar minus x bar. That's what happens. So that's going to be SSB. So what happens here? I'm taking xi bar, which is the group average. And for every line in my data, I subtract the total average. So 10 times. Basically, that's what happens. So this minus this squared. And then I do this 10 times. And I will have 10 equal numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like this. 10 equal numbers. But for the other column, these differences are going to be different, right? Because I'm taking another group average now. I'm taking this 3967 minus this, and so on. And I calculate the sum of these 40 numbers. Here, 0, sorry, 46, 5, 0, 6. So here I made it slightly better. I just wrote that we multiply 10 by this difference, because as I said, for every row, we will have the same squared deviation. Here is the result. Well, we can check that this identity holds, and the sum of squares within equals the sum of squares between, plus sum of squares between, sorry, equals sum of squares total. That's simply the illustration, that everything works and no any tricks here. Well, now we go to the hypothesis test. our null hypothesis. So basically we have all the elements to implement this hypothesis test right now. So we have the null hypothesis that means for every treatment group are equal. The alternative hypothesis states that at least one mean differs from the others. We don't know which one, but at least one of them differs. As I promised, in the next lecture, we will investigate the methods how to find this mean or several means that are different from others. Just for now, we need to claim, we need to know that there is a difference. And here is the test statistic. It's F statistic. Look, what F statistic looks like. If you remember where we used F statistic, we used F statistic to compare two sample variances, whether they are equal or not. If we take sum of squares and we divide them by the number of degrees of freedom, we will have variance, right? So therefore, SSB divided by k minus 1 is something like variance. And SSW divided by n minus k is something like variance. It's not exactly variance. It is called slightly different. So in 2 steps you will know how do we call this. But this is kind of conceptually, this is the same. Because, well, what is F statistic itself? This is something that has chi-square distribution divided by the degrees of freedom. And, well, no, sorry. F statistic was defined as something which has chi-square distribution divided by something else that has a chi-square distribution. So therefore, this thing and this thing both have exactly chi-square distribution, because those are the square deviations. So the critical region,
Sorry, you said I didn't get it. Chi-squared or
chi-squared,
wow.
yes. So what is F statistic? What is the definition of F statistic? Where was it? Lecture number 3, I guess. What is F distribution? So if you have two variables that are chi-square distributed and we divide them by the degrees of freedom, then we have F statistic, right? So what is the chi-square distributed random variable? The chi-square distributed random variable was defined as something like this.
Like a biased one. I mean, kind of.
No. So I hope that now you have some sense of these things. So anything that is related to sum of squares might be related to the chi-square. Well, more or less.
I see now. Okay.
Right? And when we divide two of these objects, there is F statistic. As I said, I skipped a lot of mathematics here just to prove that this is exactly F statistic, but I think that it's better just, to immediately show you the result instead of kind of making all these derivations. So if you are interested, the textbooks in mathematical statistics, you can open the chapter about ANOVA, and you can see why this is why this object has F distribution. Oh, you can trust me.
You just said that we assume normal distribution.
Yeah. Normal distribution of our data. But when we have a normally distributed variables and when we do some manipulations with this data, we may come to different to some other distributions. So F distribution, T distribution, chi-square distribution, all of them are based on the normal distribution. That's why we usually assume this normal distribution of the data, because only in this case we have a chance to apply all the other distributions, chi-squared, F, T, those that are familiar to us.
Okay, thank you.
So the data is normally distributed, yes. But when we manipulate with this data in the following way, when we make this sum of squares, so the sum of squares are chi-square distributed already. And when we divide this sum of squares by the number of degrees of freedom, this object, this fraction is going to be f distributed. But we believe that this f distributed only because the initial data is normally distributed, or at least we assume that it is normally distributed. So, and from the previous lecture, you remember how to work with f statistic. We need to build a critical region in the following way. So we want to calculate the quantile of f distribution, only right quantile, 1 minus alpha, such that k, and also the number of degrees of freedom, k minus 1 numerator, n minus k denominator. Why only this? As I said, we want to know that this variability between is significantly large. So that's why we, in the numerator, we take the sum of squares between, because only if the sum of squares between is large, and it probably exceeds the sum of squares within, as we see from this, we can have enough evidence to claim that the treatment has an effect on the levels of our variable of interest. So different technology leads to different productivity of oil wells. Therefore, we test that this object is greater than this object. And the critical region is this. Even though our null and alternative hypotheses are formulated differently, but basically we test the hypothesis about variances. That's why it's called ANOVA. So we can denote the numerator in the following way, and we can call this mean square between. So we usually use this acronym MS for mean squares. So mean square between, and MSW in the denominator is called mean square within. So sum of squares divided by the degrees of freedom. So F can be reformulated as this. Well, now when we have all the elements for our test, let's conclude with the following. Usually in statistics, in econometrics, you will see a lot of this table, or more or less similar table. So this table has all the elements of this ANOVA test. And try to comprehend this table in a correct way. So first column has either, in this case, we call this source, or sometimes you will see exactly between, within, and total. These three familiar words: between, within, and total. So df stands for degrees of freedom. These are just denominators here and here, k minus 1 and n minus k. So basically, with the help of this table, you can understand that there are 3 plus 1 groups, because it's k minus 1, right, in the denominator here. Therefore, 3 plus 1 groups is 4. And 36 is what? 36 is n minus k. So 40 observations in total in our table, minus 4 groups, gives us exactly 36. And the total degrees of freedom is 39. 3 plus 36.
Why did you say that it is between, but it is like error? Why?
Well, look, this notation is comes from this statistical model that we formulated. So VELS is the variability because of this alpha, And error is the variability because of epsilon. And also when we call this between and within, so between variation, so the variation between is attributed to alpha and variation within is attributed to epsilon. So that's why, as I said, you can use in this table either some, how to say, some comprehensive names, like this is the variability because of vels, and this is variability because of error, that epsilon, right? Or you can use this variability between and variability within. So within, variability within is the variability because of the error. So that's why. Or maybe I didn't get your question.
No, it's correct. Yes, thank you.
So now, sum of squares. We took them from the previous slide. Sum of squares between, sum of squares within this, and the total sum of squares. So now we take mean squared between. So this is 0.4650 divided by 3 from the previous slide. And this is mean squares within, which is sum of squares within divided by 36 here. And the last step is F statistic, which is mean squares between divided by the mean squares within. So this is how simply you can use this ANOVA table, and you can see all the data that is used in order to produce this result. So now we have this F statistic. What we need to do, we need to find what is the critical value of F statistic. So let alpha be 5% as usual. And the critical value, which is 95th quantile of F distribution with 3 numerator and 36, sorry, it must be 36, my bad. Yeah, because it's gonna be denominator degrees of freedom. So it's 3 and 36. Let me correct this. And the rejection region is such that F statistic must exceed this critical value. So what do we see? We see that our F statistic exceeds the critical value, therefore we reject the null hypothesis. So practically, what does this mean that we reject the null hypothesis? There is a significant difference in daily oil extraction for the observed 4 oil wells. But the problem for us is that we don't know which oil well differs from the others, or maybe several of them are different from the others. And that's what we are going to do in the next lecture, how to identify which oil well exactly differs and in which direction, either worse or better productivity. So, are there any questions regarding these calculations?
No, not really.
Yes, except for
I
the
guess.
probably tedious calculations which are based on the large data. Otherwise, if you have something like this, it's gonna be simple. So the most important thing is to calculate the sum of squares here and here. But don't worry, so with the help of software, you will be able to calculate all the things very fast. And then once I know that you are familiar to the things, I will allow you to calculate this automatically, to build this table automatically. So maybe I can reveal you that even in Excel we have this. Just so you will see this on the exercise session with the help of Python. So I will just show you briefly, and you will see the recording how to do this for Excel. So we take our columns here, So grouped by columns, labels in the first row, output range here. And look, you see this table that I have shown you on the slides. Sum of squares, and you see that it is called between groups and within groups, not like vals and errors, but between and within. Exactly the same numbers, exactly the same degrees of freedom, mean squares, f, and also we have p-value here additionally, but you're familiar how to calculate p-values, that's quite simple. And it also shows you f critical. So that's just in 2 clicks of mouse, you can calculate everything that we have been calculating for the whole lecture. But again, I'm kind of I want to motivate you to understand how all these numbers appear here, not just, automatically to see all these things. And also we see the summary statistics. You see that these group averages are here. Exactly that we have here. So I'm not lying when I'm saying that this ANOVA table appears in many applications. So to conclude, we know how to compare means of several populations of the data and how we can come to the conclusion that, the treatment significantly affects the variable of interest. In our case, different technology significantly affects the productivity of an oil well. And the main problem, and this is the to be continued part of this lecture, so this method doesn't say anything which particular mean significantly differs from the others, or maybe several means. Well, we will continue this discussion in the next lecture together with the two-way layout. So there is an extension when we have not one treatment, but two different treatments, and we want to compare their effect. So the logic is going to be quite similar, but the techniques are going to be a bit more sophisticated. So that's all for the lecture part. And one last important thing that Vlad announced in the beginning of the lecture. So it's been a while since the last home assignment. So home assignment number 6, which is based on one sample hypothesis, is going to be available starting from Monday. If I will be successful enough, so probably it will start earlier, but as latest on Monday, and it will be available as usual till Wednesday, till Sunday midnight, March 20th. So you will see the one sample hypothesis about the population mean, right, and population proportion. So everything that we had in the topic introduction in hypothesis testing.
That one topic that was before comparing samples.
Yes,
right?
that's correct.
Okay.
So this topic. This one. Lecture 7.
Okay.
Any questions?
No.
So tomorrow we have econometrics exercise session. So we will do some more tricks in Python. And yeah, I guess that's it from my side for today.
You had a Python file for this class. What was that?
I would rather not demonstrate you those calculations because those are probably too early for you. But I will try to discuss with Klim regarding the same calculations that we did today in Python next exercise session, because definitely you would need this. So you will go through these steps on the exercise session, which is gonna be devoted for ANOVA. Don't worry.
Okay.
And also the next exercise session, they missed one from yesterday, just as probably as kind of teaser. I have created quite interesting case for you, and there is a case which is based on the real data that I collected, and that is the data for the federal officials in our country. So for the Russian federal officials who reported their property in their declarations. So you know that now all the federal officials, they must declare their property. And I calculated for 300 something people, I calculated how many cars they owned in 2013 and in 2020. And there is going to be the case when you need to test whether our federal officials have more cars in 2020 compared to 2013. So don't miss that exercise session. That's going to be a nice exercise, I guess, for you, and interesting.
Model, or you mean master?
No, exercise session for statistics. Which you missed yesterday, right? Because of clean illness. Okay, so let's stop here and see you tomorrow.
Thank you for the call.
Bye bye.
Goodbye.